5,000 kilometers beneath your feet, a sphere of solid iron roughly the size of Pluto is changing its mind about which way to turn. It has been doing this, or something like it, for a few years now. The change was not announced. No instrument rang an alarm. The iron sphere simply slowed, paused, and then began to rotate in the opposite direction relative to the surface of the planet. The discovery was published in January of 2023 in the journal Nature Geoscience, and for a few days it made headlines, and then the news cycle moved on. But the iron sphere is still there, and it is still turning the other way, and no one can tell you with certainty what happens next. This is the heart of the planet, not a metaphor. The solid inner core is the engine that powers the magnetic field that wraps the Earth in a protective envelope, shielding the surface from the charged particles that stream from the sun and from deeper space. Without it, the atmosphere would be stripped away over geologic time, the surface would become uninhabitable, and the planet would look less like a living world and more like a dry, irradiated rock. The core has been spinning faster than the mantle and crust for as long as anyone has been able to measure it, for at least decades and probably centuries, until it stopped. Hello, and welcome to Sidereal. This is a long-form sleep science channel about space, the stars, the galaxies, the invisible structures that hold the universe together, and the scientists who spend their lives trying to understand what they are looking at. Tonight we are turning our attention inward, to the planet beneath us, because something very strange is happening to our Earth. If you find value in these stories, subscribing and liking helps the channel reach more people who might want to fall asleep to the sound of the universe being slowly unpacked. In the comments, let us know where in the world you are listening from and what time it is there. We like seeing the locations scroll past a map of strangers in the dark, all awake at different hours, all listening to the same story. Tonight we are going to ask 4 specific questions. What does it mean that a sphere of solid iron the size of Pluto, sealed 5,000 kilometers beneath your feet, has started turning the other way? Why is the invisible shield that deflects the worst of the sun's radiation thinner over the South Atlantic than anywhere else on the planet? And why is that hole growing? What is actually pulling the magnetic North Pole towards Siberia at a sprint? And what happens to the systems that quietly depend on knowing exactly where it is? And when a healthy whale beaches itself on a clear stretch of coastline for no visible reason, what does that have to do with any of this? We are going to follow the evidence for each of those questions, in order, starting at the center of the planet. We begin at the center. The Earth is not uniform. It is built in layers, like an onion, each one a different composition, a different temperature, a different phase of matter. The outermost layer is the crust, a thin skin of rock ranging from about 5 kilometers thick beneath the oceans to perhaps 70 kilometers beneath the tallest continental mountains. Beneath that is the mantle, a zone of hot, slowly convecting rock that extends nearly 3,000 kilometers downward, carrying heat from the deep interior toward the surface at a pace measured in centimeters per year. Beneath the mantle lies the outer core, roughly 2,200 kilometers thick, composed primarily of liquid iron and nickel at temperatures that exceed 4,000 degrees Celsius. And at the very center, suspended in that ocean of liquid metal, is the inner core, a solid sphere about 2,440 kilometers across, with a surface area comparable to the continent of Antarctica, a mass that accounts for less than 2% of the Earth's total, but a gravitational influence that reaches all the way to the sky. No one has ever seen the inner core. No drill can reach it. The deepest hole ever bored into the Earth's crust, the Kola super-deep borehole in Russia, reached just over 12 kilometers, barely a scratch on the planet's skin, less than 0.2% of the distance to the center. Everything we know about the core comes from seismology, from the way earthquake waves travel through the body of the planet and emerge on the other side, transformed by what they have passed through. There are 2 kinds of seismic waves that matter here. Primary waves, known as P waves, are compression waves. They push and pull material in the direction they are traveling, like sound waves in air. They can pass through both solid and liquid. Secondary waves, known as S waves, are shear waves. They shake material perpendicular to their direction of travel, and they cannot pass through liquid at all. When an earthquake strikes somewhere on the planet, seismometers on the opposite side of the globe detect the arrival of P waves that have traveled through the core, but S waves that would have passed through the liquid outer core are blocked. The shadow they cast is how we know the outer core is liquid. That shadow was first explained in 1936 by a Danish seismologist named Inge Lehmann. At the time, the prevailing model held that the Earth's core was a single uniform sphere, entirely molten. Lehmann, working largely alone at the Royal Danish Geodetic Institute, noticed something the existing model could not account for: faint seismic waves arriving inside the supposed shadow zone, where a fully liquid core should have blocked them completely. She proposed that there was a second boundary deeper down, that the core was not one body but two, an outer layer that was liquid and an inner sphere that was solid, dense enough and under enough pressure to bend and transmit waves the simple model said should not exist. Her paper, titled simply P', ran to only a few pages. It took years and considerably more data from instruments she did not have access to before the wider seismological community accepted that she was right. The Earth's solid inner core, the object this entire story circles back to, was not discovered by a large institution or a famous name. It was found by one scientist looking carefully at data nobody else had thought to question. The inner core is also not the featureless, uniform sphere a first description makes it sound like. Detailed seismic studies through the 1990s and 2000s revealed that its eastern and western hemispheres are not identical. Seismic waves traveling along the planet's spin axis move noticeably faster through one half than the other, a difference that has come to be called the inner core's hemispheric asymmetry. The boundary between the two halves does not line up neatly with the geographic equator or any obvious surface feature. It runs along a roughly north-south division instead, for reasons still not fully agreed upon. The leading explanations involve the pattern of convection in the liquid outer core surrounding it, the idea being that iron crystallizes onto the inner core's surface at different rates on each side, depending on how the overlying outer core flow happens to be organized, producing two hemispheres that are subtly different in grain structure, even though they are the same material, formed by the same basic process, at the same depth. It is one more reminder that the simplest available description of the inner core, a smooth, featureless ball of iron, is a useful starting point, and nothing more. The closer anyone looks, with better instruments and more patient analysis, the less uniform it turns out to be. The way P waves speed up and bend as they enter the inner core is how we know that sphere is solid, a crystal of iron under pressure so immense, roughly 3.5 million times atmospheric pressure at the surface, that it cannot melt despite temperatures that would vaporize rock. The inner core is not a relic, frozen at the planet's formation. It is, by most current models, still growing. As the planet slowly loses heat, the liquid outer core continues to crystallize onto the surface of the inner core, adding perhaps a millimeter of new solid iron every few hundred years. At that rate, the inner core as we know it has taken roughly the last half of the planet's history to reach its current size, and it will go on growing for billions of years after anyone is left to wonder about it. For most of the 20th century, even after Lehmann's discovery, the inner core was treated as a static object, a dense, hot anchor at the center of the planet, fixed in place. But in 1996, two seismologists at Columbia University published a paper that changed that picture again. Xiaodong Song and Paul Richards were studying seismic waves from earthquake pairs that had occurred decades apart in the same location. If the inner core was static, waves traveling through it along the same path should take exactly the same amount of time, regardless of when the earthquake occurred. But they did not. The waves from the more recent earthquakes arrived slightly faster, by about 0.3 of a second, than the waves from the older ones. The only plausible explanation was that the inner core was rotating, and rotating faster than the mantle and crust above it. The numbers they calculated were striking. The inner core, they proposed, completes one full extra rotation relative to the surface roughly every 400 years. It is not a dramatic speed, a little over 1 degree per year, but it meant that the solid iron heart of the planet was in motion, sliding against the liquid outer core that surrounds it, driven by the electromagnetic coupling between the core and the magnetic field it generates. The discovery made the inner core a dynamic place, a world within the world, with its own motion and its own relationship to time. For nearly 3 decades, the super-rotation model held. It was refined, debated, complicated by other findings, but the basic picture remained. The inner core spins faster than the surface. Then, in January of 2023, Xiaodong Song The same scientist who had first detected the rotation published a new study with his colleague Yi Yang at Peking University. They had analyzed seismic waves from the 1960s to the present, using a larger dataset and more stations than the 1996 study. What they found stopped them cold. Around 2009, the inner core's differential rotation had paused. The travel times that had been decreasing for decades suddenly leveled off and then began to shift in the opposite direction. The inner core now appears to be rotating slightly slower than the mantle, moving backward relative to the surface, for the first time since anyone has been able to measure it. The finding was not uncontested. John Vidale, a seismologist at the University of Southern California, has approached the same question from a different angle, using seismic waves generated by underground nuclear test explosions conducted by several nations during the Cold War. Those explosions, unlike earthquakes, occur at precisely known times and locations, which makes them unusually clean point sources for studying how the deep Earth has changed over the decades since. Working from that record, he has argued that the inner core's motion is not a long-term superrotation reversing course, but an oscillation, a periodic wobble with a cycle of roughly 6 years, driven by gravitational coupling between the inner core and the mantle. In Vidale's model, the apparent reversal is not a new, alarming departure. It is simply one phase of a back and forth that has been going on for a long time, and that we only noticed once we had enough decades of data to see the shape of the cycle. The two models are not fully reconciled. The scientific conversation is ongoing, and it is happening right now, with new studies appearing regularly as seismologists revisit old data and apply new techniques. But even Vidale's oscillation model implies a core that is more dynamic, more interactive, and more capable of changing its behavior on human timescales than anyone would have guessed a generation ago. Whether the reversal is a long-term shift or a 6-year cycle, the fact remains. The largest coherent object inside the planet, the Pluto-sized iron crystal at the center of the world, is in motion relative to the ground beneath our feet. And that motion is not constant. It changes. It has changed, and that matters, because the inner core is not an isolated object. It is the dynamo. The Earth's magnetic field is generated by the motion of liquid iron in the outer core, driven by convection heat rising from the inner core, cooling near the boundary with the mantle, and sinking again combined with the rotation of the planet, which organizes that motion into large-scale flows. This is the geodynamo, and it is what gives Earth its magnetic shield. The solid inner core sits at the heart of that dynamo, and its rotation influences the geometry and intensity of the field. Change the core's motion, and you change the field. Change the field, and you change everything that depends on it. Navigation, communication, the radiation environment at the surface, and the invisible architecture that life on this planet has been built inside for billions of years. So the question that opened in January of 2023 is not simply an academic puzzle about the interior of a planet. It is a question about whether the protective envelope around that planet is stable and what happens if it is not. The magnetic field has been weakening for a long time, and we know this with unusual precision because of a deliberate decision made nearly 2 centuries ago. In the 1830s, the German mathematician and physicist Carl Friedrich Gauss, working with the explorer and naturalist Alexander von Humboldt, helped organize an international collaboration that came to be called the Magnetic Union, a network of observatories across Europe and beyond, all agreeing to take simultaneous, standardized magnetic readings at fixed times of day so that researchers in different countries could finally compare measurements against each other rather than against nothing. Gauss had already worked out the mathematics needed to describe the planet's magnetic field as a whole, not just at one location, and the Union gave that mathematics something to act on, a continuous, comparable record. That record, refined and extended ever since, is why we can say with confidence that the global dipole moment, the strength of the main magnetic field, the part that aligns roughly with the planet's spin axis, has fallen by about 9% since 1840. That is roughly 180 years of data, and in that span, the field has shed nearly 1/10 of its intensity. At the current rate of decline, extrapolated forward without any change in trend, the field would drop to half its present strength in roughly 1,200 years. But the decline is not smooth, and it is not evenly distributed. The South Atlantic Anomaly is the most dramatic expression of that unevenness. It is a region stretching from roughly Chile to Zimbabwe and across to South Africa, where the magnetic field at the surface is about 1/3 of its normal strength. Satellites passing through it experience a sudden drop in the protective magnetic barrier that normally deflects the high-energy particles trapped in the Van Allen radiation belts. The particles dip closer to the atmosphere. Electronic circuits are bombarded. Astronauts on the International Space Station have reported seeing flashes of light in their eyes, cosmic rays striking the retina directly when they pass through the region. The Hubble Space Telescope, one of the most sensitive instruments ever placed in orbit, is routinely shut down during passages through the South Atlantic Anomaly. Its operators on the ground at the Space Telescope Science Institute in Baltimore plan the telescope's observing schedule around the anomaly. Certain detectors are turned off. Observations are paused. The telescope flies through the region blind and then wakes up on the other side. None the worse, but a few minutes of data shorter. It has been doing this for decades. The anomaly is not new, but it is growing, and it is deepening. The European Space Agency launched a constellation of 3 identical satellites in 2013, a mission called Swarm, designed specifically to map the Earth's magnetic field at unprecedented resolution. Each satellite carries a magnetometer, an instrument that measures the strength and direction of the field, and they fly in carefully orchestrated orbits that let them separate the contributions from the core, the crust, the oceans, and the ionosphere. Swarm has been watching the South Atlantic Anomaly for more than a decade now, and what it sees is not reassuring. The anomaly has split into 2 distinct lobes, one centered over South America and one over the South Atlantic, and the field minimum, the deepest point of the hole, has weakened by roughly another 5% just since Swarm began its observations. On a map of the global magnetic field, the anomaly looks like a bruise. It covers a significant fraction of the southern hemisphere, and it is growing westward, extending toward the Pacific. The question that sits behind every paper published on the anomaly is simple and hard to avoid. Is this the beginning of something larger? Earth has done this before, more than once. The paleomagnetic record preserved in volcanic rocks that lock in the direction of the magnetic field as they cool shows that the field has reversed polarity many times over the planet's history. In the last 2.6 million years alone, there have been at least a dozen full reversals, plus numerous shorter excursions, temporary flips or near flips that last a few hundred to a few thousand years before the field swings back to its original orientation. The last full reversal, the Brunhes-Matuyama, occurred about 780,000 years ago. The most recent well-studied excursion, the Carrington Event, happened about 41,000 years ago and lasted only a few centuries, during which the field dropped to roughly 5% of its normal strength. There was an earlier one too, around 30,000 years ago, recorded in lake sediments near Mono Lake in California, weaker and less well understood, but pointing to the same basic fact. This is not a planet that holds one fixed magnetic configuration forever. It is a planet that drifts toward instability every so often, and then finds its way back. During a reversal, the dipole field does not vanish overnight. It weakens over centuries, perhaps millennia, and the simple 2-pole structure breaks down into a complicated tangle of multiple poles scattered across the globe. The protective shield thins dramatically. The radiation environment at the surface becomes harsher. Aurorae appear not just at the poles but at mid-latitudes, even near the equator. And then, slowly, the field rebuilds, with north and south swapped. It is worth saying plainly what the fossil record does and does not show about these events. Despite a dozen or more full reversals over the last few million years, there is no clear, agreed-upon evidence linking any of them to a mass extinction or a sudden collapse of life on the surface. Whatever stress a weakened field puts on a planet, it has not, in the deep past, been the kind of stress that ends species outright. That is not a guarantee about the future. It is simply what the record actually shows, stated without embellishment in either direction. No one can say with confidence whether we are in the early stages of a reversal now. The current weakening is real, and it is accelerating relative to the longer geologic pattern. The South Atlantic Anomaly is consistent with the kind of field behavior seen in computer simulations of the geodynamo. The field could just as easily recover as it has from past excursions that did not proceed to a full flip. The honest answer is that we do not have enough data or a complete enough theory of how the geodynamo behaves to know what comes next. What we do have is a series of measurements that point in a consistent direction, The core is changing its motion. The field is weakening unevenly, and the unevenness itself, the jerks, the stripes frozen into the sea floor, the spikes locked into ancient ice, turns out to have its own story about exactly how confident anyone can be in any of the numbers this story has just given you. There is one more piece of the magnetic field's behavior worth naming on its own, because it illustrates just how much of this story has only become visible in the last 50 years, purely because someone finally had enough continuous data to notice a pattern hiding inside what had always looked like noise. In the late 1970s, two French geophysicists, Vincent Cortillot and Jean-Louis Lemuel, were studying decades of records from magnetic observatories across Europe when they noticed something the smooth, slowly declining field this story has mostly described did not predict: sudden, sharp changes in the rate at which the field was changing, visible as a kink in the data, sometimes lasting only a year or two, at specific moments rather than as part of any steady long-term trend. They called these geomagnetic jerks, and the name has stuck. A jerk is not a reversal, and it is not part of the broader, gradual 9% decline already described. It is something faster and more local, an abrupt change in the field's acceleration, as though the planet's slowly evolving signal had briefly, almost imperceptibly, stuttered. Jerks have since been identified going back through the historical observatory record to at least the 1800s, occurring every few years on no fixed schedule, sometimes visible at observatories across an entire hemisphere, and sometimes confined to a much smaller region. Their cause is still debated, but the leading explanations point, again, to the outer core, specifically to sudden, localized bursts of fluid motion near the top of the liquid core, close to the boundary with the mantle, where small disturbances in the flow can produce a brief, sharp signal at the surface, even though nothing resembling a reversal or a long-term shift is actually underway underneath it. Some researchers have proposed a connection between jerks and fluctuations in the length of day discussed earlier in this story, on the theory that whatever disturbs the flow enough to produce a jerk at the surface might also be capable of nudging the angular momentum exchanged between the core and the mantle. The correlation is suggestive in some of the data and absent in other stretches of it, which is itself a fair summary of where this particular question currently stands. A real, repeatedly observed phenomenon with a plausible general explanation and no fully settled account of the exact mechanism producing any one specific jerk. What jerks mainly demonstrate, for the purposes of this story, is how much texture sits underneath what looks, from a distance, like a single, smooth decline. The 9% drop in the dipole field since 1840 is real, and so is the broader weakening over the South Atlantic, and so is the pole's acceleration towards Siberia, but none of those slower, larger trends unfold as a clean, continuous slide. They unfold through a constant low-level static of smaller, faster, less predictable events layered on top, most of them too brief and too localized to notice without decades of dense observatory data, and someone deliberately looking for exactly this kind of irregularity. The field is not simply declining, it is declining unevenly, in fits and starts, on top of a background of constant small disturbance that researchers are still learning to read in any detail. One more honest item on the list of things known to be happening, without yet being fully understood. Everything this story has said about past reversals, the Brunner-Matuyama event, the Lachamp excursion, the rough dozen full flips recorded over the last 2.5 million years, rests on a record that had to be discovered before anyone could read it. And the way it was discovered is its own story, sitting at the intersection of the magnetic field and an entirely different scientific argument that was, for most of the 20th century, deeply unsettled, whether the continents move at all. By the 1950s, research ships equipped with magnetometers towed behind them on long cables had begun surveying the ocean floor in earnest, mapping the strength of the magnetic field at the sea surface as they went, mostly in the hope of finding mineral deposits or simply filling in blank spots on otherwise featureless charts of the seabed. What they found instead, particularly along the mid-ocean ridges, the underwater mountain ranges, where new ocean floor is actively forming, was a pattern no one had expected. Long, parallel stripes of alternating magnetic intensity, running roughly parallel to the ridge itself, mirrored almost exactly on either side of it, like a barcode stamped into the rock. The explanation arrived from two directions nearly at once, which is itself part of why the resulting idea carries three names rather than one. In 1963, two researchers at Cambridge University, Fred Vine and his graduate supervisor Drummond Matthews, proposed that the stripes were a direct record of the Earth's magnetic field reversing over time, captured permanently in the rock as it cooled. Molten rock rising at a mid-ocean ridge contains tiny magnetic mineral grains that align themselves with whatever direction the ambient field happens to be pointing at. The moment the rock solidifies and cools below a certain temperature, as new crust continues to form at the ridge and spreads symmetrically outward in both directions, the physical mechanism behind continental drift. Though that idea was still controversial at the time, each new strip of rock locks in the field's orientation at the moment of its birth. A normal polarity field produces one kind of stripe. A reversed field produces its mirror opposite. The seafloor, in this picture, behaves like a continuously running tape recorder, laying down a parallel, symmetric record of every reversal the planet has gone through for as long as that stretch of ocean floor has existed. A Canadian geophysicist named Lawrence Morley had arrived at essentially the same explanation independently and at almost the same time, and submitted a paper describing it to two separate journals before Vine and Matthews published theirs. Both rejected it. One reviewer reportedly dismissed the idea as the kind of speculation better suited to a cocktail party conversation than a scientific journal. Morley's version never appeared in print until well after Vine and Matthews had already published the same basic idea and received the credit that came with being first into a journal rather than first to the idea itself, which is why the hypothesis is now usually called, a little awkwardly but more fairly, the Vine-Matthews-Morley hypothesis, an acknowledgement, arriving decades late, that being right and being published are not always the same achievement. The hypothesis answered two enormous questions at once, which is part of why it mattered so much once it was finally accepted. It explained the striped magnetic pattern on the seafloor, and it provided exactly the kind of independent, physical evidence that the seafloor spreading idea proposed a few years earlier by the American geologist Harry Hess, and the broader theory of continental drift it supported, which had been argued over and largely dismissed by mainstream geology for the previous half-century, since the German meteorologist Alfred Wegener first proposed it had been missing. If the magnetic stripes truly were a tape recording of reversals, and if the same reversal sequence appeared in the same order, on both sides of a ridge, and on ridges in entirely different oceans, then the seafloor had to be spreading apart, and continents had to be moving, because no other mechanism could produce a perfectly mirrored, internationally consistent record like that. Surveys through the rest of the 1960s confirmed exactly this. The same sequence of stripes, in the same relative widths, on ridge after ridge around the planet. Plate tectonics, an idea that had been treated for decades as fringe geology, became, within the space of a few years, the organizing framework for the entire discipline. For the purposes of this story, the more direct payoff is this. The striped seafloor is the instrument that lets scientists date the reversal record this script has been relying on. Because the rate at which new ocean floor forms and spreads outward from a ridge can be measured independently, using other dating methods on the rock itself, and cross-checked against the orderly, predictable widening of the stripes moving away from the ridge axis. The width of each magnetic stripe translates directly into a length of time. Wider stripes mean the field held one orientation for longer before flipping. Narrower stripes mean a shorter interval between reversals. Reading outward from any mid-ocean ridge, in either direction, is, in a very literal sense, reading backward through the planet's magnetic history, one stripe at a time, with the oldest readable seafloor anywhere on Earth dating back only to the Jurassic, because anything older has already been recycled back into the mantle at a subduction zone somewhere, the seafloor's own version of a tape eventually running out and being erased to make room for more. This is also, incidentally, why the inner story of this whole script connects back to itself in a way that is easy to miss on a first listen. The Brunhes-Matuyama reversal, the Lassomp excursion, the broader timeline of roughly a dozen reversals in the last 2.5 million years, all of it was pieced together, stripe by stripe, from exactly this seafloor record, decades before anyone had detected the inner core's rotation pausing, decades before satellites watched the South Atlantic Anomaly deepen, decades before anyone thought to ask whether the pole's drift towards Siberia might be connected to any of it. The reversal record came first, recovered from rock dragged up from the ocean floor and read with a magnetometer towed behind a ship. Everything this script has described about the field's recent, faster-than-usual changes is, in a real sense, a new chapter being written on top of a tape that was already running, quietly, for the entire span of the planet's geological history, and that someone only learned to read a little over 60 years ago. The seafloor stripes are not the only independent check on the reversal record this story keeps returning to, and the second method comes from a completely different direction. Not rock, but ice and trees. When the magnetic field weakens, more cosmic radiation reaches the upper atmosphere, and some of that radiation strikes nitrogen and oxygen atoms in ways that produce specific, rare isotopes, beryllium-10 and carbon-14 among them, at a measurably higher rate than during periods when the field is strong. Beryllium-10 produced this way eventually settles out of the atmosphere and is locked into snow as it falls, compacting over centuries into the layered ice of Greenland and Antarctica, each layer datable by counting downward the same way a tree's rings are counted inward. Carbon-14 follows a parallel path into the carbon cycle, taken up by living trees and locked into their growth rings as the wood forms. Both isotopes, independently, show a sharp spike around the time of the Lachamp excursion, roughly 41,000 years ago, exactly the period during which the seafloor and lake sediment record already showed the field dropping to a fraction of its normal strength. The ice core spike and the rock-based reversal record were established using entirely different physical processes, measured by entirely different research communities, decades apart, and they agree. That agreement is, in its own quiet way, one of the more reassuring facts in this entire story. When two unrelated lines of evidence, each capable of being wrong in its own particular way, land on the same date for the same event, the event becomes very difficult to argue away as an artifact of either method individually. The same isotope record has been used to identify and date excursions and brief weak field intervals that do not show up as cleanly in the seafloor stripes, because some events were simply too short or too irregular to leave a clear, wide stripe on spreading crust that may have been moving at an inconvenient rate at the time. Ice cores, recording centuries in fine, countable layers, rather than kilometers of slowly accumulating rock, can sometimes resolve detail the seafloor record smooths over. Between the two methods, researchers have built a far more confident timeline of the field's recent weak points than either approach could have produced alone. One more example, in a story full of them, of an answer that took two independent and very different kinds of patient, careful looking before anyone could be reasonably sure of it. On the morning of the 1st of September, 1859, an English brewer and amateur astronomer named Richard Carrington was at his private observatory south of London, sketching a large group of sunspots when he saw something no one had documented before. A patch of intense white light flared up suddenly within the sunspot group, brightened for several minutes, and then faded. Carrington had, without realizing the full significance of it at the time, become the first person to observe a solar flare. He reported the sighting to the Royal Astronomical Society, noting carefully that he did not expect anyone to believe a connection between what he had seen and anything happening on Earth. He did not have to wait long to find out he was wrong. About 17 hours later, a geomagnetic storm struck the planet with a force that remains, more than a century and a half later, the largest such event ever recorded with instruments. Telegraph systems across Europe and North America, the most advanced electrical infrastructure of the age, were overwhelmed. Operators reported sparks jumping from their equipment. In some stations, the induced current was strong enough that operators disconnected their batteries entirely and continued sending messages powered only by the storm itself. At least one telegraph office reported its paper catching fire. Aurorae, normally confined to high latitudes, were seen as far south as Cuba, Hawaii, and Colombia bright enough in some locations that people reportedly read newspapers by their light at midnight. The Carrington Event, as it came to be called, happened at a moment in history when the only large-scale electrical infrastructure on the planet was a network of telegraph wires. The damage was real but limited, because there was not yet very much for a storm of that size to damage. That is no longer true. A modern Carrington-scale event would arrive in a world threaded with high-voltage power grids, satellite constellations, shipping and aviation that depend on satellite positioning, and financial systems that run on precise, continuous timing. Several national academies and insurance research groups have modeled what a storm of that magnitude would do to today's infrastructure, and the estimates, while uncertain, converge on a common shape. Localized transformer failures in vulnerable power grids, satellite outages, and orbital decay for spacecraft caught at the wrong altitude, and an economic cost running into the hundreds of billions of dollars concentrated in the days and weeks it would take to repair the most damaged ground equipment. The planet does not have to imagine this entirely from an 1859 baseline. In July of 2012, a coronal mass ejection of comparable strength to the Carrington Event erupted from the Sun and crossed the orbital path of the Earth. It missed. The eruption occurred at a point in the Sun's rotation when the Earth happened to be on the far side of its orbit by the calculations of Daniel Baker, a space physicist at the University of Colorado Boulder, who studied the event using data from one of NASA's solar observation spacecraft. The Earth had simply not yet arrived at the place in space the storm passed through. Had the eruption occurred about a week earlier or later in the Sun's rotation, the storm would have struck a planet with a far more extensive electrical and satellite infrastructure than existed in 1859, and the consequences would have been measured in years of recovery rather than days. This is the context in which the South Atlantic Anomaly and the broader weakening of the dipole field matter most directly. The magnetic field is not a uniform wall. It is thicker in some places and thinner in others, and a storm of Carrington-scale energy does not check which part of the shield it is about to hit. A planet whose overall field has already lost roughly a tenth of its strength, and whose weakest point is already measurably thinner than the rest, is not approaching the next large storm from the same position of protection it occupied 2 centuries ago. None of this means a storm is coming on any particular timeline, or that the next one will be worse because of the field's decline. Specifically, the relationship between field strength and storm impact is complicated and depends heavily on where on the globe a given storm's effects are concentrated. What it does mean is that the shield's overall condition is one more variable feeding into a risk that used to be calculated against a steadier baseline and now has to be calculated against a moving one. The storms this story has been tracing the Carrington Event above all, but also the routine, far gentler background hum of solar wind streaming past the planet every single day, all produce the same visible signature at high latitudes: the aurora. It is worth pausing on what the aurora actually is, because for most of recorded history no one knew, and the way the answer was finally worked out is itself one of the better stories in the history of the magnetic field this whole script has been describing. The aurora is light given off when charged particles from the Sun, guided by the Earth's magnetic field lines, are funneled down toward the poles and collide with gas molecules high in the atmosphere, oxygen and nitrogen. Mostly, excited by the impact and releasing that energy as a glow, green and red from oxygen, blue and purple from nitrogen, depending on altitude and the energy of the particles involved. The reason it concentrates near the poles rather than spreading evenly across the sky is the same reason a magnet's field lines bunch together at its ends. The Earth's magnetic field channels incoming particles down 2 roughly circular zones, one around each pole, called the auroral ovals, which expand toward the equator during a strong geomagnetic storm and contract back toward the poles when things are quiet. For most of human history, this was attributed to anything but physics. Indigenous peoples across the Arctic developed their own explanations, many treating the lights as spirits or ancestors. European folklore variously cast them as omens of war or disease. The first person to connect the aurora seriously to the magnetic field was the Norwegian physicist Christian Birkeland, working in the early years of the 20th century. He built what he called a Torella Latin for Little Earth, a small magnetized sphere suspended inside an evacuated glass chamber, and bombarded it with streams of electrons fired from a cathode. Photographed in the dark, the electrons did exactly what he suspected they should. They curved along the model's magnetic field lines and converged into 2 glowing rings near the sphere's poles. A laboratory aurora, built on a desk, decades before satellites existed, to confirm that the same physics was playing out on a planetary scale above the real poles. Birkeland went further than the demonstration. He proposed that the particles producing the real aurora were not simply ambient cosmic rays, but a continuous stream coming specifically from the Sun, and that they followed organized electrical currents running along the magnetic field lines connecting the upper atmosphere to far more distant regions of space currents. now called Birkeland currents in his honor, confirmed directly by satellite measurements only in the 1970s, well over half a century after he first proposed them from Torella experiments and ground-based magnetic surveys conducted across Scandinavia and the Arctic, often in punishing winter conditions, with instruments built largely by his own small team rather than purchased from established manufacturers. It took the wider physics community decades to accept what the simple model in his lab chamber had already suggested. The aurora is not a separate phenomenon from the storms this story keeps returning to. It is the same magnetic field, the same charged particles, the same coupling between sun and planet, made visible. This connection matters directly for understanding the SAA and a weakening dipole, because the field does the same channeling job everywhere, all the time. Not only during a storm, under ordinary, quiet conditions, the magnetic field deflects the bulk of the solar wind around the planet entirely, funneling only a narrow, organized stream down toward the poles, which is what produces the aurora as a relatively gentle, contained, beautiful phenomenon, rather than a planet-wide bombardment. Where the field is thinner, as it now measurably is over the South Atlantic, that channeling is less effective, and more of the incoming radiation environment reaches lower altitudes than the standard picture of aurora confined to the poles would suggest. This is part of why the Hubble Space Telescope shuts down specifically over that one stretch of ocean, and why astronauts report the unsettling sensation of seeing light inside their own eyes when they pass through it. They are, in a narrow but real sense, catching a private, localized echo of the same physics that produces the aurora, just delivered through a gap in the shield rather than through the deliberate funnel the field provides everywhere else. During a full magnetic reversal, were one to happen, the orderly two-pole structure that gives the aurora its familiar shape, two neat rings, one at each end of the planet, would not survive intact. Paleomagnetic reconstructions of past reversals suggest the field fragments into several weaker, wandering poles during the transition, which would scatter the aurora across a far less predictable pattern of locations, possibly visible at far lower latitudes far more often for as long as the transition takes to complete. No one alive has seen this happen. The historical record of strong but ordinary storms, including Carrington's, is the closest available preview aurora over Cuba and Hawaii for one extraordinary night in 1859, rather than the years-long disordered pattern a genuine reversal would likely produce. It is a difference of degree and duration, not of underlying mechanism, and it is one more thread tying the planet's interior directly to something a person can actually stand outside and look up to see. Birkeland did not live to see most of this confirmed. He died in 1917, more than 50 years before satellites measured the currents he had proposed, from a glass chamber and a magnetized model the size of a grapefruit. The Torella sits, in a sense, alongside Lehmann's seismograms, as one of this story's clearest examples of the gap between knowing and understanding, closing slowly, one careful observer at a time, often working with equipment that looks almost too modest for the scale of what it eventually proved. The same heat that drives the geodynamo and generates the magnetic field has another, entirely separate way of reaching the surface, and it produces some of the most geologically strange real estate on the planet. Most volcanoes sit at the boundaries between tectonic plates, where one slab of crust grinds against, dives beneath, or pulls apart from another, and the mechanism is straightforward: friction, pressure, and melting rock finding a way up through a crack that plate motion itself has opened. The Hawaiian Islands break that rule entirely. They sit in the middle of the Pacific Plate, thousands of kilometers from any plate boundary, and yet the islands are volcanically among the most active places on Earth. The explanation is a mantle plume, a narrow, persistent column of unusually hot rock rising from deep within the mantle, possibly originating near the boundary with the core itself, staying more or less fixed in one place for tens of millions of years, while the rigid plate above it slides slowly across the top. The Canadian geophysicist John Tuzo Wilson proposed this explanation in 1963. At almost exactly the same moment, seafloor magnetic stripes were forcing geology to accept that the plates moved at all. Wilson noticed that the Hawaiian Islands were not a random scatter of volcanoes, but a precise age sequence. The active volcanoes sit at one end of the chain, on the youngest island, while progressively older, increasingly eroded, and ultimately submerged volcanic remnants stretch away in a long, curving line stretching thousands of kilometers across the ocean toward the northwest, each one older than the last, the entire chain running all the way to a string of seamounts near the Aleutian Trench that are tens of millions of years old. If the plate is sliding steadily across a fixed source of heat anchored deep in the mantle, this is exactly the pattern that source would leave behind: a volcanic conveyor belt, stamping a new island onto the plate every so often as the old ones are carried away and slowly subside beneath the waves, extinct, while a new one rises to take their place. The current active island, sitting directly above the plume today, will eventually be carried off the hotspot in its turn, just as every island before it was, and a new one is already forming on the seafloor nearby to replace it. Hawaii is the textbook case because the trail is so clean and so well dated, but it is not the only hotspot, and not every hotspot sits conveniently in open ocean. Yellowstone, in the western United States, sits above a continental hotspot whose plume has left its own age-progressive trail, not a chain of islands, because there is no ocean to form islands in, but a chain of calderas stretching back across Idaho, evidence of where the same fixed heat source sat beneath the North American plate millions of years before the plate's drift carried the present-day Yellowstone caldera into position above it. The supervolcano that occasionally features in disaster documentaries is, in this framework, simply the most recent stop on a trail the plate has been dragging itself across for roughly the last 17 million years. The same basic physics as Hawaii's island chain, only with a far thicker, more silica-rich continental crust, producing a very different, far more violent style of eruption when the plume's heat finally does break through. Exactly how deep these plumes originate, and whether all of them share a single common cause, remains an active and genuinely unsettled area of research. Another honest item on this story's running inventory of what is not yet fully understood. Some geophysicists, working from seismic tomography, the technique of using earthquake waves to build a three-dimensional image of the mantle's interior structure, in roughly the way a hospital CT scanner images a body, have traced certain plumes, including the one beneath Hawaii, downward through images that suggest a connection running all the way to two enormous, anomalous structures sitting near the core mantle boundary itself, vast regions beneath Africa and the Pacific, where seismic waves travel unusually slowly, suggesting rock that is hotter or chemically different, or both, than the surrounding mantle. Other researchers argue the evidence for plumes reaching that deep is weaker than it looks, and that many apparent hotspots are better explained by shallower processes in the upper mantle that do not require any direct pipeline all the way down to the core. The debate has not been settled, and the honest position, consistent with how this entire story has tried to treat its uncertainties, is that the plumbing connecting the surface to the deepest interior of the planet is real in at least some cases, suspected in others, and not yet mapped with the same confidence as the magnetic field or the reversal record. What is well established is the broader principle the plumes illustrate, regardless of exactly how deep their roots go. The same heat budget that drives convection in the outer core generates the geodynamo and ultimately powers the magnetic field. This entire story has been tracing, also finds other ways to escape the planet, and hotspot volcanism is one of the clearest. The core is not only the engine behind an invisible magnetic shield, it is also, indirectly, the engine behind a chain of Pacific islands old enough that the oldest of them have eroded back beneath the waves, and behind a slow-motion volcanic trail across the Rocky Mountains that happens to currently sit underneath one of America's oldest national parks. Both are surface evidence of the same interior process this story keeps returning to. Heat, generated and stored at the center of the planet, finding its way outward by whatever path is available, on whatever timescale that particular path allows. The same mid-ocean ridges that record the planet's magnetic reversals, stripe by stripe, turn out to be doing something else entirely at the same time, something no one suspected until a research submarine went looking for something unrelated and found it by accident. In February of 1977, a team of geologists diving in the submersible Alvin to the Galapagos Rift, a section of mid-ocean ridge in the Pacific roughly 2.5 kilometers down, was there to study the geology of seafloor spreading directly the same process behind the magnetic stripes, observed this time with human eyes through a viewport rather than read off a magnetometer towed behind a ship on the surface. What they found instead, clustered around cracks in the seafloor where mineral-rich water near 400 degrees Celsius was venting directly into the near-freezing deep ocean, was life. dense colonies of organisms entirely unknown to science, clams the size of dinner plates, mussels in thick mats, and most strikingly, meter-long tube worms with no mouth, no gut, and no obvious way to feed themselves, clustered in fields so dense the scientists on board reportedly struggled, in the moment, to believe what the cameras were showing them. The explanation took biologists somewhat longer than the geology had taken to work out, and it overturned an assumption so basic that no one had previously thought to state it as an assumption at all, that essentially all life on Earth depends, directly or indirectly, on sunlight. Photosynthesis, the conversion of light into stored chemical energy, sits at the base of almost every food chain anyone had ever studied. Plants and algae, capturing sunlight, everything else eating them or eating something that ate them, all the way up. The communities clustered around these vents, 2.5 kilometers beneath any sunlight could possibly reach, were not running on that system at all. They were running on chemosynthesis. Bacteria living symbiotically inside the tube worms' bodies, and free living in mats around the vents themselves, that derive energy not from light but from oxidizing hydrogen sulfide, the same toxic, rotten egg-smelling compound that would poison most surface life, dissolved in the scalding vent water as it mixes with cold seawater and reacts with dissolved oxygen. The worms have no need for a mouth or a gut because their entire nutritional strategy is to host these bacteria internally and absorb the products of that chemical reaction directly. The whole ecosystem, base to top, runs on chemistry rising from inside the planet rather than light falling from outside it. This mattered for reasons well beyond marine biology. It demonstrated, for the first time with direct, observable evidence rather than theoretical argument, that a complete, self-sustaining ecosystem could exist entirely independent of the sun, powered instead by the same heat. This entire story has traced back to the core, escaping at exactly the kind of seafloor spreading center where new magnetic stripes are continuously being laid down. The heat driving the chemical reactions that feed these vent communities is, ultimately, heat from the planet's interior, carried up through the mantle and released where new crust is forming, the same fundamental energy source behind the geodynamo and the hotspot volcanism this story described earlier, simply expressed here as scalding mineral water rather than a magnetic field or a chain of Pacific islands. The discovery also reshaped, almost immediately, how seriously scientists were willing to consider the possibility of life surviving elsewhere in the solar system, in places far too cold, far too dark, or far too chemically hostile for anything resembling a sunlit surface ecosystem. If a stable, complex food web could be built entirely on chemical energy rising from a planet's interior rather than light from its star, then the same basic principle might apply somewhere far less hospitable than the floor of the Pacific, beneath the ice crust of a moon like Europa or Enceladus, for instance, where tidal heating rather than radioactive decay keeps a liquid ocean from freezing solid, and where any analogous chemistry rising from a rocky seafloor far below that ice might, in principle, support something similar. None of this has been confirmed anywhere beyond Earth. It remains, for now, a possibility raised directly by what a handful of geologists in a cramped submersible happened to notice while looking for something else entirely. In 1977, at the bottom of the Pacific, more vent fields have been found since, along ridges in the Atlantic, the Indian Ocean, and elsewhere in the Pacific, each with its own particular mix of species, some shared across vent fields thousands of kilometers apart, in ways that are still not fully explained. How a chemosynthetic shrimp or a particular species of vent crab manages to colonize a new vent field, isolated by enormous stretches of inhospitable open ocean from the nearest other vent, remains an active area of research in its own right. What is settled is the basic principle. The heat escaping at a mid-ocean ridge is not simply a geological curiosity recorded in striped rock. It is, in at least a handful of well-documented places, the foundation of an entire, independently evolved branch of the tree of life. Running on the same interior engine that drives everything else this story has described, expressed here in its most literal and most directly observable form, life, built from the planet's own internal heat, with no need for the sun at all. This is where the next part of the story begins. Not at the core, not in the radiation belts, but at the top of the world, where the magnetic North Pole has been drifting for more than a century, and where, Sometime in the last few decades, that drift turned into a sprint. The North Magnetic Pole is not the same thing as the geographic North Pole. The geographic pole is the point where the Earth's rotation axis intersects the surface, a fixed location in the Arctic Ocean, marked by ice that drifts and reforms with the seasons. The magnetic pole is the point where the geomagnetic field lines are perpendicular to the surface, pointing straight down. It moves because the field that generates it is generated by a turbulent, convecting liquid, and turbulence does not sit still. Long before Ross or Amundsen went looking for the pole itself, sailors already knew that a compass needle does not point at true geographic north from most places on Earth, and that the size of that error, the declination, changes depending on where you are standing, more slowly on when. The English astronomer Edmund Halley, better remembered today for the comet that carries his name, took this seriously enough to lead 2 Atlantic voyages between 1700 and 1702, specifically to measure declination at sea, and in 1701 he published the result as what is generally considered the first isogonic chart, a map connecting points of equal magnetic declination with curving lines across the entire Atlantic basin, intended as a practical aid for navigators trying to correct their compass bearings without having to rediscover the error from scratch on every voyage. Halley understood, correctly, that the chart would eventually go stale because the field producing the declination was itself slowly changing. He simply had no way to predict by how much or how fast 2.5 centuries before satellites would let anyone track that change directly. Sailors and explorers worked the pole's existence out using a simpler version of the same basic instrument Halley's surveys depended on, a magnetized needle mounted to swing freely in a vertical plane rather than the horizontal swing of an ordinary compass, a dip circle. Near the magnetic pole, the needle points almost straight down into the ground. The closer you are, the steeper the dip. Early explorers who sought the pole using exactly this method, James Clark Ross in 1831, Roald Amundsen in 1903, found it in different places in the Canadian Arctic both times, but never quite where the previous expedition had left it. The difference confirmed what physicists had already suspected from the broader pattern of compass readings collected across the world. The pole was on the move. But for most of the next century, it moved at a stately pace, roughly 10 kilometers a year, slow enough that a sailor correcting a compass reading for magnetic declination, the angle between true north and magnetic north at a given location, could use the same correction for years before it needed updating. Then, sometime in the 1990s, the pole began to accelerate. By the early 2000s, it had reached roughly 40 kilometers a year. It crossed the international dateline in the later 2010s, leaving the Canadian Arctic behind and heading out across the Arctic Ocean towards Siberia, and by 2015, its speed had climbed past 50 kilometers a year, faster than it had moved in at least 4 centuries of recorded observation. The trajectory was not a wobble or a wander. It was close to a straight line, aimed at the Russian coast. The acceleration caught the attention of the people responsible for the World Magnetic Model, the global mathematical description of the geomagnetic field that underlies everything from smartphone compasses to military navigation systems to the runway numbering at airports. The model is built and maintained jointly by the United States National Centers for Environmental Information and the British Geological Survey, working alongside a parallel international effort called the International Geomagnetic Reference Field, coordinated through the International Association of Geomagnetism and Aeronomy, so that the scientific community has more than one independent description of the same moving target to check against. Both models are updated on a 5-year schedule under normal circumstances. The previous World Magnetic Model update had come in 2015. The next was due in 2020, but by early 2018, the gap between the model's predicted pole position and the position satellites were actually measuring had grown large enough that navigation systems relying on the model were beginning to degrade in real time, well before the scheduled update was due. Arnaud Chouliat, a geomagnetist at the University of Colorado and at NOAA's Cooperative Institute for Research in Environmental Sciences, was the lead scientist on the World Magnetic Model team that had to make the call. In a review meeting in 2018, Chouliat and his colleagues looked at the latest readings from the swarm satellites and from ground observatories and concluded that the 5-year model they had produced in 2015 was already too far out of date to trust. The pole had simply moved farther, faster than anyone building the model had accounted for. They faced an unusual choice for a body that normally works on a fixed schedule: release an emergency update out of cycle, something that had never been done before in the model's history, or let the error keep growing until the regular 2020 update. They chose the emergency release. In January of 2019, the updated model placed the North Magnetic Pole at 86.5 degrees north, 162.9 degrees east, deep in the Arctic Ocean, closing in on the Russian continental shelf, and still moving. The reason the pole is heading toward Siberia and not somewhere else has to do with the shape of the magnetic field where it meets the bottom of the mantle. The field at the surface is not generated uniformly across the core. It emerges instead from a small number of concentrated patches called flux lobes, where the magnetic field lines bunch together and are unusually intense. In the northern hemisphere, there are two dominant lobes, one beneath Canada and one beneath Siberia. For most of the past several centuries, the Canadian lobe was the stronger of the two, and the pole stayed anchored near it. But the Canadian lobe has been weakening for decades, while the Siberian lobe has been strengthening, and the pole, which behaves, in effect, like something being pulled toward whichever source is currently stronger, has been migrating toward Siberia as the balance between the two has shifted. This pole drift is a different phenomenon from something with a similar sounding name that occasionally gets confused with it: true polar wander, in which the solid body of the Earth itself slowly reorients relative to its spin axis over millions of years, driven by the redistribution of mass in the mantle. That is real. It is documented in the rock record, and it has nothing to do with what is happening to the magnetic pole on a human timescale. The magnetic pole's sprint towards Siberia is a feature of the fluid, turbulent outer core, changing its internal pattern over decades fast by geological standards. Glacial by any standard a person actually experiences, but fast enough that the institutions responsible for keeping global navigation systems accurate have had to abandon a 5-year update schedule that had worked for the better part of a century. The consequences are not abstract. Airport runways are numbered according to their magnetic heading, rounded to the nearest 10 degrees and divided by 10. When the magnetic field drifts far enough, a runway's heading relative to magnetic north changes enough to require a new number. In January of 2011, Tampa International Airport closed its main runway for about a month, specifically to repaint it. What had been designated 18 right and 36 left became 19 left and 1 right, a direct consequence of magnetic drift outpacing the airport's last repainting. It was not an isolated case. Airports in several countries have made the same correction since, and more are expected to need it as the pole continues its current path. Military navigation systems that rely on magnetic bearings require periodic recalibration for the same reason. The electronic compass built into most smartphones queries the world magnetic model silently, many times a day, correcting the raw reading from its internal magnetometer to point at true north rather than magnetic north. And for a stretch of months around any model update, that correction is working from data that is already slightly behind the pole's actual position. The pole's migration is, in the end, a visible signal of something invisible. The same core motion that paused and may have reversed the inner rotation is reshaping the magnetic field at the surface, and the North Magnetic Pole is the clearest tracer available of that deeper process, the moving shadow of something happening 5,000 kilometers down in a place no instrument has ever directly touched. And there is more, because the core's influence does not stop at the magnetic field. It extends to the very spin of the planet, the rotation that defines the length of every day and night you have ever lived through. And the spin, it turns out, is changing too. In the summer of 2020, the Earth began to spin faster than it had in decades. Not by much. In absolute terms, the difference was measured in milliseconds, but by enough that the clocks noticed. The atomic clocks that define coordinated universal time, kept in temperature-controlled volts at national laboratories around the world, tick with a precision that loses less than 1 second in 100 million years. They are the metronome against which the planet's rotation is measured, and in 2020 they recorded something the timekeeping community had not expected to see. The Earth was consistently completing its daily rotation faster than 24 hours, day after day, with a frequency and magnitude that broke records stretching back to the beginning of the atomic clock era in the 1960s. The length of a day has never been a fixed quantity, and we know this on timescales far longer than instruments have existed, because the planet's own biology kept a record before anyone thought to ask the question. Certain fossil corals grow in daily bands, the way trees grow in annual rings, and a geologist named John Wells showed in the 1960s that counting those bands in corals roughly 400 million years old produces something close to 400 days in a year rather than the present day 365. The coral record is not the only evidence reaching back before anyone had a clock precise enough to measure the difference directly. Astronomers, including Richard Stephenson, working through the latter 20th century, combined ancient eclipse records from Babylonian clay tablets and Chinese court astronomers, some more than 2,000 years old, with modern calculations of exactly where and when those eclipses should have been visible given the planet's current rotation rate. The two did not quite line up. The ancient observers recorded eclipses visible from cities that, by today's rotation rate, should have been in darkness or daylight at the wrong moment for that particular eclipse to be seen there at all, a discrepancy that vanishes neatly once you allow for a day that was very slightly shorter, accumulating into hours of difference over 2 millennia of compounded small change. Two completely different kinds of evidence, one carved into coral skeletons hundreds of millions of years old, the other copied by hand onto clay and bamboo a little over 2,000 years ago, to arrive at the same basic conclusion. The length of a day is not a fixture of the planet. It is a slowly drifting number, readable in the growth bands of long-dead reef animals and in the careful, dutiful eclipse records of court astronomers who had no idea what their observations would eventually be used to prove. The number of days has been shrinking, and each one has been growing longer for the entire span of life on this planet, because the moon's gravity creates tidal friction that gradually slows the Earth's spin. That long, steady deceleration is the backdrop against which the 2020 acceleration is so unusual. The trend that has held for 400 million years briefly ran the other way, because the Earth was, for most of the atomic clock era, spinning slightly slower than 24 hours exactly. The accumulated gap between atomic time and the time kept by the planet's actual rotation occasionally required inserting a leap second, an extra second, added to coordinated universal time, usually at the end of a year, to keep the two timescales from drifting too far apart. Since 1972, 27 leap seconds have been added, the most recent in 2016. Then the trend reversed. 1994 had briefly held the record for the shortest day since atomic timekeeping began. In 2020, the planet beat that record 28 separate times. The single shortest day ever recorded came in July of that year, completing in just over a millisecond less than 24 hours. The accumulated effect was large enough that the International Earth Rotation and Reference Systems Service, the organization responsible for tracking the planet's orientation, which does this in part using a technique called very long baseline interferometry, comparing the arrival times of radio signals from distant quasars at observatories scattered around the globe to fix the Earth's orientation against the most stationary reference points available anywhere in the universe, began seriously discussing something that had never happened before: a negative leap second, removing a second from the global clock rather than adding one. No negative leap second has ever been implemented. Many of the systems that depend on precise time synchronization, satellite positioning networks, financial trading networks, telecommunications infrastructure, power grids were built to handle the insertion of an extra second. Almost none of them were built with code to handle the subtraction of one. The mere possibility was enough to trigger a string of quiet, urgent conversations among timekeepers and software engineers through the early 2020s. In November of 2022, the international body that governs the world's system of measurement, the General Conference on Weights and Measures, voted to resolve the uncertainty directly. Leap seconds, in their current form, are to be phased out entirely by 2035, removing the mechanism altogether, rather than deciding case by case whether to add or subtract. The cause of the 2020 acceleration is still being worked out, but the leading explanations all point back to the distribution of mass within and on the planet. The Earth's rotation rate depends on its moment of inertia, the resistance of a spinning body to changes in its spin, the same principle that makes a skater spin faster when she pulls her arms toward her body and slower when she extends them. Move mass closer to the rotation axis and the spin speeds up. Move it farther away and the spin slows down. Several large processes are redistributing the planet's mass right now, in different directions. Greenland and Antarctica are losing ice at accelerating rates, and that water, once locked up near the poles, spreads out across the global ocean, moving mass away from the rotation axis, which should slow the spin down, not speed it up. Counteracting that is glacial isostatic adjustment, the slow rebound of the crust in places like northern Canada and Scandinavia, still rising back up centuries after the ice sheets that depressed it during the last glaciation finally melted away. As that crust rises, mass shifts subtly inward and upward, nudging the moment of inertia in the other direction. And running underneath both of those is the same mechanism this whole story keeps returning to: core-mantle coupling. The inner and outer core are not isolated from the mantle above them. They exchange angular momentum with it through electromagnetic and gravitational forces, and changes in the core's rotation, including, potentially, the same pause and reversal that opened this story, can transfer momentum to the mantle and crust, speeding the whole planet up or slowing it down by amounts too small to feel and just large enough to measure. There is a separate, older puzzle worth naming here, precisely so it does not get folded into this one by accident. In 1891, an American astronomer named Seth Carlo Chandler discovered that the Earth's rotation axis itself wobbles slightly relative to the crust, tracing a small circle roughly every 433 days, a real, well-documented motion now called the Chandler wobble. It is not the same thing as the length of day variation this story has been tracing. One is about how fast the planet spins. The other is about which way its axis points while it does. They are driven by related but distinct physics, and conflating them is one of the easiest mistakes to make when reading about the Earth's rotation. The wobble has been measured continuously for more than a century. The length of day acceleration is the newer, stranger development, and it is the one that connects most directly back to the core. The timekeeping community is still assessing what the 2020 acceleration means for the planet going forward. The Earth has since slowed slightly from that peak, but it remains faster than its long-term average, and the decision to retire leap seconds altogether by 2035 is, in part, an acknowledgement that the old, simple correction mechanism was never built for a planet whose spin could change direction of trend with so little warning. What 2020 made clear is that the ground beneath your feet is not a stable platform in any absolute sense. It is a participant in a continuous, invisible exchange of momentum with the deepest interior of the planet, an exchange happening right now at a level too small to feel but large enough that the guardians of global time have begun keeping notes they did not expect to need. The core paused. The field is weakening unevenly. The pole is racing across the Arctic Ocean. The planet's spin sped up and has only partly settled back down. These are not separate stories. They are different surfaces of a single interconnected system, the geodynamo and the rotating Earth, linked by electromagnetism and gravity, responding to each other on timescales from years to millions of years. The question that follows is what happens to everything else, the atmosphere, the oceans, the living world, when the dynamo changes its rhythm. The atmosphere is the next layer outward from the surface, and it is changing too, not just in the familiar ways of greenhouse warming near the ground, but at its highest reaches, where the air thins to near nothing and the sky turns black even in daylight. The mesosphere, the layer between 50 and 85 kilometers up, is cooling and contracting, and the satellites that cross through it are feeling the difference. The mesosphere is the most alien layer of the atmosphere that still counts as part of the sky. It begins about 50 kilometers above the surface, above the clouds, above the weather, above the altitude where commercial airliners level off at the top of the stratosphere. The air there is so thin that a human being exposed to it would lose consciousness in seconds and die within minutes, not chiefly from cold, though it is cold, but from the simple absence of enough oxygen molecules to sustain cellular respiration. The pressure is less than 1/10,000th of the pressure at sea level. A breath drawn there would contain essentially nothing. By international convention, the boundary most often used to mark the edge of space, the Kármán line sits at about 100 kilometers, only slightly above the top of the mesosphere itself. The layer this story is tracing is, in a real sense, the last stretch of recognizable sky before there is no sky left to speak of. And yet, by volume, the mesosphere is one of the largest regions of the atmosphere. It extends from 50 kilometers to roughly 85, a 35-kilometer band that wraps the entire planet, and for most of human history, it was almost entirely unknown. Weather balloons cannot reach it. Aircraft cannot fly in it. Rockets pass through it in seconds on their way to orbit, too fast to linger and measure. It was not until the space age that we began to understand what happens there, and what we have found is a region of the sky that is cooling and contracting at a rate that was not predicted, for reasons that are only partly understood. The cooling of the mesosphere is a direct consequence of the same carbon dioxide that warms the lower atmosphere. Near the surface, carbon dioxide traps infrared radiation that would otherwise escape to space, warming the planet. But in the thin, dry air of the upper atmosphere, the physics works differently. Carbon dioxide molecules absorb energy from the surrounding air and radiate it away into space. They do not collide frequently enough with other molecules to redistribute that energy as heat. The net effect is that carbon dioxide acts as a coolant in the mesosphere, radiating away more energy than it absorbs, and as carbon dioxide concentrations have risen from about 280 parts per million before the industrial era to more than 420 parts per million today, the mesosphere has responded by getting colder. The numbers are drawn from a long-running satellite mission called TIMED, the Thermosphere, Ionosphere, Mesosphere, Energetics and Dynamics mission, launched by NASA in 2001. On board is an instrument called SABRE, the sounding of the atmosphere using broadband emission radiometry, which measures the infrared emissions from carbon dioxide in the upper atmosphere, and from those measurements derives temperature profiles from the stratosphere all the way to the edge of space. SABRE has been watching the mesosphere for more than 20 years now, and the trend is clear. The mesosphere has been cooling at about 1.5 to 2 degrees Celsius per decade, roughly 3 times faster than the surface has been warming, which makes the mesosphere one of the most rapidly changing thermal environments on the planet. The cooling has a mechanical consequence. Cold gas contracts. As the mesosphere cools, it shrinks, and the altitude of the mesopause, the top of the mesosphere, the boundary where it gives way to the thermosphere, is dropping. A study published in the Journal of Geophysical Research. Atmospheres in 2022 estimated that the mesopause has fallen by roughly 1 to 2 kilometers since the 1980s. The entire upper atmosphere is settling downward, the sky itself thinning under the influence of a gas we cannot see. This contraction might seem like an abstraction, a curiosity for atmospheric physicists, until you consider what passes through the mesosphere every day. Low Earth orbit, where the International Space Station flies and where the vast majority of operational satellites reside, begins at an altitude of about 160 kilometers. But many satellites fly lower, in very low Earth orbit, skimming the upper reaches of the atmosphere at altitudes where the air, though tenuous, still exerts drag. The mesosphere sits below that band, but the thermosphere above it is affected by the same carbon dioxide cooling, and the long-term trend across the upper atmosphere is a gradual contraction that reduces atmospheric drag on satellites over time. For decades, satellite operators factored that slow, predictable reduction into their orbital planning. The complication is that the atmosphere does not respond only to carbon dioxide. It also responds to the sun on a much shorter timescale, and the two effects do not always pull in the same direction. On the 3rd of February, 2022, SpaceX launched a batch of 49 Starlink satellites from the Kennedy Space Center in Florida, a routine launch, one of many in a steady cadence, building out a constellation meant to provide global broadband coverage. The satellites were placed into a low insertion orbit at about 210 kilometers, intending to use onboard thrusters to climb to their operational altitude of roughly 550 kilometers. A day after launch, a coronal mass ejection from the sun struck the Earth's magnetic field, intensifying the aurora and, less visibly, heating and expanding the thermosphere. The storm that arrived was a moderate one by space weather standards, the kind that occurs hundreds of times in a typical solar cycle. But at the satellite's low insertion altitude, the thickened atmosphere was enough. Atmospheric drag increased sharply. The small thrusters could not compensate. 38 of the 49 satellites lost too much altitude to recover and burned up in the atmosphere within days, a loss running to tens of millions of dollars. The episode was a short-term expansion, the opposite of the long-term cooling trend, but both point to the same underlying fact. The upper atmosphere is a dynamic, responsive system whose behavior is changing in ways that do not always match the models built to predict it. With the number of active satellites and pieces of tracked debris in low orbit continuing to grow, Researchers who study orbital congestion have warned for years about the long-term risk of a runaway cascade of collisions, sometimes called Kessler syndrome, after the NASA scientist who first modeled it, a risk that becomes harder to manage precisely when the atmosphere's drag on objects at a given altitude is less predictable than it used to. Need 8. There is another, gentler effect of the cooling mesosphere, visible to anyone who lives at high latitudes and looks up after sunset on a clear summer night. Noctilucent clouds, night-shining clouds, form at the mesopause, around 83 kilometers up, where the air is 1,000 times thinner than at the summit of Mount Everest, and the temperature, even in summer, can drop below -120 degrees Celsius. They are made of ice crystals, water vapor freezing onto particles of meteoric dust, and they glow a pale electric blue because they are so high that the sun, already below the horizon for an observer on the ground, still illuminates them directly. They hover at the edge of space for a few hours in the deepening twilight, a cold blue against a darkening sky. Noctilucent clouds were first documented in 1885, 2 years after the eruption of Krakatoa, and for a long time they were assumed to be volcanic in origin. They persisted long after the volcanic aerosols had settled, and through the 20th century they became a regular feature of summer skies at latitudes above 50 degrees north. Then, around the turn of the 21st century, they began appearing farther south than anyone had recorded before, photographed from Colorado, from Utah, from Northern California, and they became brighter and more frequent overall. NASA launched a satellite in 2007 called AIM, the Aeronomy of Ice in the Mesosphere, designed specifically to study these clouds from orbit, and over more than 15 years of operation, it has recorded a steady increase in the presence of water ice at the edge of space, attributed to 2 related causes: the cooling of the mesosphere itself, which makes it easier for ice crystals to form, and a rise in water vapor reaching the upper atmosphere, partly from the oxidation of methane, a greenhouse gas that breaks down into water molecules at high altitude. The noctilucent clouds are, in a sense, a signature of a changing planet, written in ice at the boundary between air and space. The mesosphere is a quiet region. No one lives there. No crops grow there. It does not flood, or burn, or shake. And yet its contraction is one of the most unambiguous signals that the planet's atmosphere is being altered from top to bottom, from the surface where we breathe to the edge, where the sky gives way to the void. The changes there do not stay there. They alter the orbits of satellites. They change the chemistry of the upper atmosphere. They are part of the same interconnected system this story has been tracing from the core outward, and what happens in one layer rarely stays confined to that layer. The planet's great fluid shells, the core, the atmosphere, are not the only ones in motion. The ocean is the thickest of them, a layer of liquid water averaging about 3.7 kilometers deep, covering more than 70% of the Earth's surface, and it moves heat around the globe on a scale that dwarfs anything the atmosphere can manage on its own. The ocean is the planet's circulatory system, and its largest current is showing signs of critical instability. The Gulf Stream is a river within the sea. It is part of a larger system called the Atlantic Meridional Overturning Circulation, or the Overturning Circulation, a vast loop of moving water that begins in the tropics, where the sun heats the surface ocean to a bath-like warmth, evaporating water and leaving behind saltier, denser water. That warm, salty water flows north along the eastern coast of North America, past Florida, past the Carolinas, past Newfoundland, and then arcs across the North Atlantic toward Europe. As it travels north, it releases heat into the atmosphere, roughly 1 billion megawatts of thermal energy, more than 100,000 times the output of a large nuclear power plant, enough to keep the winters in London and Paris and Berlin 10 degrees Celsius warmer than they would be at the same latitude in North America. By the time the water reaches the Norwegian Sea and the waters south of Greenland, it has cooled so much that it becomes dense enough to sink. It plunges to the deep ocean and begins the long journey back south, a cold, deep return flow that travels along the seafloor all the way to the Southern Ocean, where it rises and eventually rejoins the surface circulation. The whole loop takes about 1,000 years to complete. This circulation has been running, in some form, for millions of years. It is driven by differences in temperature and salinity, the thermohaline circulation, in the language of oceanography, and it is one of the primary reasons the Earth's climate is as stable as it is. The overturning circulation transports roughly 20 million cubic meters of water per second, a flow rate equivalent to about 100 times the combined discharge of every river on Earth. It redistributes heat from the tropics to the high latitudes. It ventilates the deep ocean, bringing oxygen to the abyssal waters. It regulates the global carbon cycle by burying organic matter in deep-sea sediments. It is, in a very real sense, one of the organ systems of the planet, and it is slowing down. The evidence for the slowdown comes from several independent lines of measurement, the most direct of which is a piece of scientific infrastructure most people have never heard of. Since 2004, an international collaboration anchored by the National Oceanography Centre in Southampton in the United Kingdom, working with American partners, including the Woods Hole Oceanographic Institution, has maintained a line of moored instruments stretching across the Atlantic at 26 degrees north, roughly the latitude of the Bahamas, continuously measuring the strength of the overturning flow in something close to real time. The project is called RAPID, and it exists for exactly this reason. Rather than waiting for indirect signals to accumulate, it puts sensors directly in the current and asks how strong the heartbeat is this month, this year, compared to the last. What RAPID and the other lines of evidence around it show is a current that has weakened over the period of direct observation, consistent with a longer decline that other methods push back further in time. Sea surface temperatures in a region south of Greenland, an area oceanographers have taken to calling the warming hole because it has not warmed in step with the rest of the North Atlantic and has in some seasons actually cooled, were identified as a likely fingerprint of a weakening overturning circulation in a 2015 paper by Stefan Rahmstorf, a climate scientist at the Potsdam Institute for Climate Impact Research in Germany. Rahmstorf's group argued that a slowing current would leave exactly this signature: less warm water reaching the far North Atlantic and a patch of relative cold sitting where the rest of the basin was warming around it. Sediment cores from the seafloor, which preserve a record of ocean circulation stretching back millennia, indicate that the slowdown began in the mid-20th century, around the time industrial greenhouse gas emissions began to accelerate. In February of 2021, a study published in the journal Nature Geoscience by Niklas Boers, also at the Potsdam Institute, went further than describing a trend. Boers and his colleagues analysed sea surface temperature and salinity data across the Atlantic, looking specifically for the statistical fingerprints that physical systems display as they approach a tipping point, not just decline, but a loss of resilience, a system that takes longer to recover from small perturbations than it used to. They found those fingerprints. The overturning circulation, they concluded, has lost stability. It is no longer simply fluctuating around a steady mean. It is approaching a threshold beyond which it could shift abruptly to a much weaker state, or shut down outright. The word abruptly here is doing real work and deserves to be taken at its actual meaning. In climate science, abrupt can mean decades, sometimes less, and the paleoclimate record contains more than one example of exactly this kind of fast collapse. The clearest is the Younger Dryas, beginning about 12,800 years ago. The Earth had been emerging from the last ice age, temperatures rising, ice sheets retreating, ecosystems adjusting to a warming world when, in what amounts to a geological instant, the warming stopped. The northern hemisphere was plunged back into near-glacial conditions. Temperatures in Greenland dropped by roughly 10 degrees Celsius. The forests that had been recolonizing Europe retreated. Megafauna, already under pressure, woolly mammoths and saber-toothed cats among them, slid further toward extinction. The cold period lasted more than 1,000 years before the climate abruptly warmed again. The leading explanation is a massive pulse of fresh water into the North Atlantic, released when a glacial lake called Lake Agassiz broke through the retreating Laurentide ice sheet that had been damming it. The flood of fresh water reduced the salinity and density of the surface ocean enough that it stopped sinking in the far north. The overturning circulation shut down. The heat engine that had kept northern Europe relatively mild simply stopped running, and the consequences cascaded through the global climate system, shifting monsoon belts, drying the tropics, locking in a colder, harsher world for over 1,000 years. The Younger Dryas was not a one-off in the deeper glacial record. Through the last ice age, sediment cores show a recurring pattern now called Heinrich events, named for the German marine geologist Hartmut Heinrich, who first identified them. Episodes when massive armadas of icebergs broke off the ice sheets, ringing the North Atlantic and drifted out to sea, dumping enormous volumes of fresh water and rock debris as they melted, disrupting the overturning circulation each time in roughly the same way the Younger Dryas event did, on a scale that left a visible fingerprint in seafloor sediment that geologists can still read today. The Younger Dryas is not a perfect analogue for the present moment. The ice sheets ringing the North Atlantic are far smaller now than they were 12,000 years ago. The ocean as a whole is warmer, and the atmospheric carbon dioxide concentration is nearly twice what it was then, but the basic physics has not changed. Add enough fresh water to the North Atlantic from the accelerating melt of the Greenland ice sheet, from increased precipitation in a warmer atmosphere, from thinning Arctic sea ice and the density of the surface water drops. Drop the density far enough, and the water stops sinking. Stop the sinking, and the overturning circulation weakens. Weaken it past a certain point, and the paleoclimate record says it does not fail gently. A full collapse, if it occurred, would reshape the climate on both sides of the Atlantic. Northern Europe would face winters 5 to 10 degrees Celsius colder than today, closer to those of present-day Siberia. Monsoon systems that bring rain to hundreds of millions of people across West Africa, South Asia, and East Asia would shift, with the potential for severe drought in some regions. Sea level along the eastern coast of the United States would rise by perhaps an additional ½ meter to a meter as the ocean adjusts to the loss of the current's gravitational and dynamic pull on water levels. The Intergovernmental Panel on Climate Change, in its most recent assessment, rated the probability of a full collapse before the year 2100 as low but not negligible, and noted separately that the current is almost certain to weaken further over the coming decades, even under moderate emissions scenarios, with consequences that will be felt well before any full collapse, if one happens at all. What connects this to the rest of the story is the pattern, not any single cause. The core is changing its motion, the magnetic field is weakening, unevenly, the poles are shifting, the planet's spin sped up and has only partly settled, the upper atmosphere is contracting, and now the great ocean conveyor, one of the fundamental regulators of the climate that has allowed human civilization to flourish for the last 10,000 years, is slowing toward a threshold it has crossed before, in a world that existed long before agriculture, before cities, before writing. These changes are not happening in isolation from each other in any causal sense the science currently supports. They are happening to the same planet, at the same moment, through different mechanisms, and the ocean is not the end of the chain. It touches the life that moves through it, and that life is responding to. The grey whale makes one of the longest migrations of any mammal on Earth. Each year, the eastern North Pacific population travels from feeding grounds in the Bering and Chukchi Seas, north of the Aleutian Islands, down the west coast of North America, to the warm, shallow lagoons of Baja, California, where the females give birth. The southward journey covers roughly 10,000 kilometers. The northward return, with new calves, covers the same distance in reverse. The whales navigate this route with a precision that allows them to return to the same lagoons, the same stretches of coastline, generation after generation, without visible landmarks, without the stars, through water that can be turbid and dark for weeks on end. The mechanism by which they do this is not fully understood, but the leading hypothesis is magnetoreception, the ability to sense the Earth's magnetic field and use it as a map. Cetaceans, the order that includes whales and dolphins, carry deposits of magnetite, an iron oxide mineral that is strongly magnetic, in their tissues, often concentrated in regions of the head and brain. The crystals are small, on the scale of nanometers, and they are believed to function as a biological compass, responding to the direction and intensity of the ambient magnetic field and transmitting that information to the nervous system. A whale swimming through the ocean would, in this model, sense the magnetic topography beneath it, the ridges, the anomalies, the subtle gradients in field strength that form a kind of invisible landscape, and use that awareness to stay on course. The problem is that the magnetic landscape is not fixed. It changes. The field weakens. The poles drift. Anomalies grow and split. If a whale's internal map was calibrated to a particular magnetic topography, and that topography shifts, the map becomes wrong. In 2020, a study published in the journal Current Biology examined the relationship between grey whale strandings and solar activity. The researchers, led by Jesse Granger at Duke University, analyzed 31 years of stranding data from the west coast of the United States, covering 186 individual strandings of otherwise healthy grey whales, animals that were not sick, not malnourished, not entangled in fishing gear. They compared the timing of these strandings to measurements of solar radio flux, a proxy for solar storm activity that also correlates with disturbances in the Earth's magnetic field, and found a statistically significant relationship. On days with high solar radio flux, the probability of a grey whale stranding increased by roughly a factor of 4. The effect was strongest during the southward migration, when the whales are navigating toward a specific target, the Baja Lagoons, rather than the more diffuse northward return. The implication is not that solar storms strand whales directly. It is that solar storms disturb the magnetic field, and the disturbed field interferes with the whale's ability to navigate. A whale whose internal compass is suddenly reading incorrectly may make a navigational error, turning toward shore when it should turn away, or following a magnetic contour that no longer leads where it used to lead. The stranding is not a sickness. It is a mistake made in a medium that offers few second chances. The pattern holds, less cleanly but still measurably, in strandings of sperm whales, beaked whales, and pilot whales, which cluster around geomagnetic disturbances more often than chance alone would predict. Cetaceans are not the only animals that use magnetic navigation, and they are not even the best-studied case. That distinction probably belongs to a small, unremarkable-looking songbird, the European robin. Beginning in the 1960s, the German researchers Wolfgang and Roswitha-Wilczko ran a long series of experiments showing that migratory robins kept in enclosed cages, with no stars or landmarks visible, would still orient themselves in their correct migratory direction, and that this orientation could be deliberately scrambled by altering the magnetic field around the cage or disrupted entirely by certain wavelengths of light. That second finding turned out to be the more important one. It pointed toward a magnetic sense that depends on light, which made no sense for a mineral compass like magnetite, and which eventually led researchers toward a genuinely strange explanation. A light-sensitive protein in the bird's eye, called cryptochrome, that may form pairs of molecules with unpaired electrons, whose spins are sensitive to the angle of the surrounding magnetic field. A quantum mechanical effect operating inside a living retina that can apparently last just long enough to leave a chemical trace the bird's nervous system can read as directional information. The radical pair mechanism, as it is called, remains an active and unsettled area of research, studied by groups including Henrik Moritzen's lab in Germany and others working alongside physicists rather than only biologists, because the proposed effect sits at the edge of what quantum mechanics is expected to do inside a warm, wet, chemically noisy living cell. What matters for this story is the larger point it illustrates. Magnetite is not the only way an animal can sense a magnetic field, and at least two genuinely different physical mechanisms, a mineral compass in some species, a light-dependent quantum effect in others, appear to have evolved independently to do roughly the same job. The field these animals rely on is the same field. The biology built more than one way to read it. A third, equally well-studied case belongs to the loggerhead sea turtle. Female loggerheads return, decades after hatching, to nest on the same stretch of beach where they themselves emerged from the sand, often after migratory loops spanning entire ocean basins. Kenneth Lohman, a biologist at the University of North Carolina at Chapel Hill, spent much of his career demonstrating how hatchling turtles, in laboratory experiments, can be shown to imprint on the specific magnetic signature of their home beach. Not just a general sense of north, but a fine-grained reading of the local field's intensity and inclination, distinctive enough to function as a kind of magnetic address. Decades later, adult females appear to navigate back toward that same signature, even as ocean currents and storms move them off a direct course along the way. It is, among the documented cases, one of the most precise uses of the magnetic field as a literal map, rather than a simple compass, and one of the clearest illustrations of what happens when that map is built from a field that is not actually fixed. A beach's magnetic signature drifts over the decades a turtle is alive, at a pace too slow for any individual turtle to notice, but not too slow to matter across a population's lifespan. These navigational systems evolved over millions of years inside a magnetic field that was relatively stable in its overall structure, even as it fluctuated in detail, weakened, strengthened, reversed, and recovered many times over evolutionary history. Life persisted through all of it because a reversal that takes thousands of years gives evolution time to track the change. The open question is what happens when the pace of change accelerates relative to that, while a species is already contending with habitat loss, shifting prey, and a climate moving under it for entirely separate reasons. The animals are not simply trying to navigate a shifting magnetic field in isolation, they are trying to do it in a world that has already moved their feeding grounds, altered their migration timing, and fragmented their routes for other reasons entirely. And it is not only the animals. Human beings carry magnetite in their brains as well. The discovery was made in 1992 by Joseph Kirschvink, a geobiologist at the California Institute of Technology, who had spent years studying magnetoreception in other animals and suspected humans might retain the same biological structures. Using samples of human brain tissue and a technique called high-resolution transmission electron microscopy, Kirschvink found magnetite crystals identical in structure and composition to those found in magnetotactic bacteria and in the navigational tissues of birds and fish, concentrated in regions of the brain associated with spatial orientation and memory. The finding was largely set aside for more than 2 decades. Then, in 2016, a team of researchers from the United Kingdom and the United States confirmed it using more modern techniques, finding magnetite crystals in human brain tissue in quantities and shapes, suggesting they were grown by the body itself rather than absorbed as environmental contamination. What that magnetite is actually for remains unknown. There is no evidence that humans consciously sense the magnetic field the way migratory birds or sea turtles do. A series of experiments through the 2019s and 2020s, including some from Kirschvink's own lab, have found that human brain activity may respond subtly in small, inconsistent ways, not present in every subject, to controlled changes in the direction of an ambient magnetic field, measured as a shift in alpha brainwave activity on an electroencephalogram. The effect is real in the data, but far from a conscious sense, and there is no credible published evidence connecting the planet's weakening field, or any of the viral claims circulating about it, to widespread human health effects. What the presence of magnetite in the human brain does suggest is something quieter than a hidden sixth sense. We are not separate from the planet's magnetic environment in the way it is easy to imagine. We are embedded in it. Our bodies contain the same minerals, the same crystalline structures that whales and robins and sea turtles use to find their way across entire ocean basins. Whether or not we use them consciously, they are there, responding, in whatever faint way the data show, to the same field that is weakening, the same poles that are shifting, the same invisible architecture this story has been tracing from 5,000 kilometers down. The living world is being reshaped in more visible ways too, by mechanisms that have nothing to do with magnetism and everything to do with the same carbon dioxide already discussed in the mesosphere. Trees are growing faster than they used to, because additional carbon dioxide acts as a fertilizer for photosynthesis, and across much of the planet forests are adding biomass more rapidly than they did a century ago. But the wood they produce is different. A study published in Nature Communications in 2021, led by researchers at the Technical University of Munich, examined wood density trends in European forests over the past century, and found that density has declined significantly. Trees growing faster under elevated carbon dioxide build cells with thinner walls and larger internal spaces, producing, in effect, a bigger house with weaker materials. European spruce plantations in particular are showing increased vulnerability to wind throw being blown over in storms, precisely because of the trade-off between faster growth and weaker structure that foresters are only beginning to factor into their long-term planning. The seasons themselves are shifting in step with the same warming. Spring arrives earlier than it did a generation ago by roughly 3 to 5 days per decade for many species, a trend driven by warming temperatures rather than anything happening at the core or in the field. Leaf-out dates for trees, first flowering dates for wildflowers, emergence dates for insects are all moving earlier, but not at the same rate for every species in a given ecosystem. A bird that migrates based on day length, a fixed astronomical cue rather than local temperature, may arrive at its breeding ground to find that the caterpillars it depends on have already peaked and declined, having responded to the earlier warmth on a different schedule. A wildflower that blooms early may bloom before its specialist pollinator has emerged at all. These mismatches are documented across dozens of ecosystems on multiple continents, and they are not caused by anything happening 5,000 kilometers down. They are a separate consequence of the same warming atmosphere, running in parallel with everything this story has traced through the planet's interior. The biologists who study animal navigation have a name for what happens when a magnetic map stops matching the territory: magnetic disorientation. An animal that relies on magnetic cues can usually cope with slow, gradual changes in the field. It recalibrates the way a long-haul traveler adjusts to a new time zone. What is harder to cope with is rapid, unpredictable change, layered on top of every other pressure a species is already managing. The whale strands not because it is sick, but because the road it has followed for 10 million years is no longer quite where it used to be. There is a quieter rhythm beneath all of this, one that predates the magnetic field's recent troubles by billions of years. It is not a rhythm of the core or the oceans or the atmosphere's slow contraction. It is a rhythm of electricity, a global pulse that has been ringing around the planet since the planet first had an atmosphere capable of producing lightning. It is called the Schumann resonance, and it is one of the most subtle and least understood of the Earth's natural frequencies. The Earth ionosphere cavity is a spherical shell of space bounded on the bottom by the surface of the Earth and on the top by the ionosphere, the layer of charged particles that begins at roughly 60 kilometers altitude and extends outward. The surface conducts electricity. The ionosphere conducts electricity. The air between them, mostly, does not. The result is a resonant cavity, not unlike the body of a violin, in which electromagnetic waves can bounce around the planet, reflecting off the ionosphere and the ground in turn, circling the globe many times over before they fade. The energy that drives the resonance is lightning. At any given moment, roughly 2,000 thunderstorms are active somewhere on Earth, most of them in the tropics, producing about 50 lightning strikes per second across the planet as a whole. Each strike sends a pulse of current radiating electromagnetic energy in every direction. Most of that energy dissipates locally, but a portion of it couples into the Earth ionosphere cavity and begins to travel. The particular wavelengths that fit the Earth's circumference, an integer number of times, reinforce themselves as they circle, building into a standing wave, a permanent, low background hum generated continuously by the planet's own weather. The fundamental frequency of that hum was predicted mathematically, well before anyone measured it, by the German physicist Winfried Otto Schumann in 1952. Schumann, a professor at the Technical University of Munich working in electromagnetic theory, calculated that a spherical cavity with the dimensions of the Earth ionosphere system would resonate at a fundamental frequency of roughly 7.83 Hz, derived directly from the speed of light divided by Earth's circumference. This is an extremely low frequency, well below the lower limit of human hearing, which bottoms out around 20 Hz. The Schumann resonance is not a sound a person could hear, even with perfect ears pressed directly against the right instrument. It is an electromagnetic wave, audible only after instruments convert it into a signal a speaker can reproduce. Schumann's prediction sat as an elegant piece of theory for several years before anyone confirmed it experimentally. That confirmation came in 1960 from two researchers at Bell Telephone Laboratories in the United States, Martin Balser and Charles Wagner, who built sensitive low-frequency receivers, found quiet locations free from power line interference, and detected a real, persistent signal sitting almost exactly where Schumann's mathematics said it should be, a steady pulse near 7.8 Hz, with weaker harmonics at roughly 14, 2027, and 33 Hz, matching the theory closely enough that there was no longer any doubt the Earth was, in this specific sense, ringing. The resonance is not perfectly fixed, and the reason it shifts tells you something about the cavity itself. The ionosphere's height and conductivity change with the amount of solar radiation striking it, which means the resonant cavity is effectively a different size by day than by night, taller and more conductive on the sunlit side of the planet, lower and patchier on the side in shadow. The fundamental frequency drifts by small fractions of a hertz as a result, in a daily rhythm sometimes described as the resonance breathing in step with the sun, and it shifts further during solar flares and geomagnetic storms, when the ionosphere is disturbed more dramatically. None of these shifts are large. They have been documented for decades by monitoring stations in Russia, Hungary, Japan, and the United States, and they form a continuous, well-behaved record of the planet's electromagnetic environment, one that, unlike the magnetic field this story has spent most of its time on, shows no long-term sign of weakening or becoming unstable. That stability is worth stating plainly, because it sits in tension with a great deal of what circulates online about this particular phenomenon. Claims that the Schumann resonance has begun spiking erratically to 30, 40, even 80 Hz, far above its normal frequency, and that these spikes are responsible for widespread insomnia, anxiety, or a subjective sense that time itself is accelerating, are common in certain corners of social media and wellness culture. They are not supported by published, peer-reviewed measurements. Monitoring stations such as the one operated by the Tomsk Space Observation System in Russia do record transient variations during solar storms and unusual thunderstorm activity, occasionally with split or more complex peaks, but a sustained, unexplained jump to many multiples of the fundamental frequency. The kind of behavior that would actually be anomalous has not been documented in the scientific literature, despite more than 60 years of continuous monitoring. The reason this particular natural frequency attracts so much attention, despite its stability, is almost certainly its overlap with human brainwave frequencies. The alpha rhythm, the dominant pattern in a relaxed, awake human brain, oscillates at roughly 8 to 12 Hz. The theta rhythm, associated with drowsiness and the earliest stage of sleep, sits around 4 to 8 Hz. The Schumann fundamental, at 7.83 Hz, lands almost exactly between them, a genuine coincidence and a striking one. It is natural to wonder whether some evolutionary entrainment connects the planet's electromagnetic pulse to the brain's own electrical rhythm, given that both have existed, in some form, for as long as there have been living nervous systems on a planet with an atmosphere. The evidence for any direct entrainment, however, is weak and largely anecdotal. Controlled experiments exposing subjects to the Schumann frequency under laboratory conditions have not reliably demonstrated the kind of brain activity changes the entrainment idea predicts. The human brain is, electrically, far noisier than the faint signal arriving from the ionosphere, and no established mechanism explains how that signal would influence neural activity in a meaningful way. The coincidence in frequency may be exactly that, a coincidence, interesting precisely because it invites a connection the data does not currently support. There is, separately, a genuinely strange piece of Cold War history that runs on the very same physics. Radio waves at extremely low frequencies, in the same band the Schumann resonance and its harmonics occupy, have one unusual practical property. Unlike ordinary radio frequencies, they can penetrate a meaningful distance into seawater. Submarines need to communicate without surfacing, and ordinary radio cannot reach them once they are more than a few meters down. Through the 1960s, 70s, and 80s, the United States Navy built a series of extremely low-frequency transmission systems, known at various stages by names including Project Sanguine and later Project ELF, using enormous ground-based antenna arrays, some stretching for tens of kilometers, to broadcast one-way signals to submerged submarines using exactly the slice of the electromagnetic spectrum that lightning fills naturally and continuously, for free, all over the world. The systems were eventually decommissioned as satellite and laser-based alternatives matured, but for decades, a significant piece of nuclear-era military infrastructure was built specifically to exploit the same physical band that gives the Earth its natural electromagnetic hum, a reminder that the line between a planet's background noise and a technology built to imitate it is sometimes thinner than it looks. The monitoring stations that track the Schumann resonance continue listening regardless of any of this. The Tomsk station in Russia, the Moshiri station in Japan, the Nagychenk station in Hungary, and several others record the pulse day and night, year after year, building a long baseline that will eventually reveal whether the resonance is changing in any systematic way over decades rather than hours. So far, that baseline looks stable. The variations sit within the envelope of ordinary geophysical noise. The planet's electromagnetic heartbeat, unlike its magnetic field, shows no sign of weakening or becoming arrhythmic. The instruments keep watching anyway, because that is the only way anyone would know if that ever changed. There are other sounds, though, that are not electromagnetic but acoustic, not a hum but a roar, and they have been reported for centuries by people who looked up at a clear sky and heard something that should not have been there. On a clear afternoon in the Ganges Delta, Sometime in the later 19th century, a British colonial administrator heard what sounded like a distant cannonade. The sky was empty. No ships were visible on the river. No storm sat on the horizon. The sound rolled across the water. A low, percussive boom, and then it faded, and the afternoon returned to its stillness. He asked the local residents what it was. They told him it was the Barisal guns, and that they had been hearing them for as long as anyone could remember. The Barisal guns are one of the best documented examples of a phenomenon that appears in the historical record under many names, in many places, all describing essentially the same experience. On the Finger Lakes of upstate New York, they are called the Seneca guns. In Belgium and the Netherlands, Mispuffers, fog belchers. In Japan, Uminari, the sea roaring. In the Philippines, the Ritumbos. In Italy, La Marina. In Germany, Nebel Canone. A loud, explosive sound, sometimes like a cannon, sometimes like distant thunder, sometimes closer to a sonic boom, arriving under a clear or only partly cloudy sky with no visible source, often strong enough to rattle windows and shake dishes, usually isolated rather than a sustained rumble, coming from nowhere anyone present can point to. New England has its own well-documented case, and unlike most of the others, this one has a written record stretching back further than almost any comparable phenomenon anywhere in the world. The Moodus noises take their name from the town of East Haddam, Connecticut, whose name in turn comes from a word in the local Algonquian language, Machimudus, generally translated as something close to place of bad noises. Colonial settlers in the early 1700s recorded the indigenous accounts they encountered when they arrived, describing sounds the local Wangunk people had clearly been living alongside for generations before any Europeans set foot there, and the settlers themselves went on to document the same booms and rumbles in their own letters, town records, and eventually, scientific correspondence, continuously for roughly 3 centuries. Explanations ranged from underground caverns full of trapped gas to displeased spirits, to eventually instruments. Seismologists studying the area in the 1980s installed sensors directly over the affected ground and recorded large numbers of very small, shallow earthquakes, micro-earthquakes, too weak to be felt as ground motion in the usual sense, but apparently strong enough at the right depth and rock structure to generate an audible acoustic boom without a perceptible shake. The Moodus noises turned out to have an explanation. It simply took roughly 300 years of written records, plus instruments no 18th century resident had access to get there. The difficulty with studying skyquakes more generally is that, unlike Moodus, most of them leave no comparable trace. There is no crater, no ash, no seismic signature reliable enough on its own to locate an epicenter, particularly for events that occur far from any seismometer. By the time a researcher could even begin to investigate, the sound is gone, and what remains is a shaken window and the memory of whoever happened to be there to hear it. The global network built to detect a completely different problem turns out to be the best available tool anyway. The organization responsible for enforcing the Comprehensive Nuclear Test Ban Treaty operates a worldwide array of infrasound sensors, sensitive microbarometers, capable of detecting pressure waves in the atmosphere far below the threshold of human hearing, arranged in clusters at dozens of stations around the globe, specifically so that the direction and timing of an arriving wave at several stations at once can be combined to triangulate where it came from, the same way 3 or 4 people hearing the same distant clap of thunder at slightly different times could, in principle, work out where the storm was. Built to catch clandestine nuclear tests, the network also happens to catch a great deal of natural infrasound it was never designed to study, and it occasionally picks up signals that correlate with reported skyquake events, though the correlation is frequently ambiguous, since the same instruments also catch distant explosions, meteors entering the atmosphere, and remote volcanic activity, all of which can sound remarkably similar by the time their pressure wave has traveled far enough to register. Several physical mechanisms have been proposed for skyquakes, and each one probably accounts for some genuine fraction of the reports, without any single mechanism explaining all of them. The most straightforward is distant thunder, ducted unusually far by a temperature inversion, a layer of warm air sitting above a layer of cold air, which can bend sound waves back down toward the ground over distances of 100 kilometers or more, far past where the storm producing them would normally be audible or even visible above the horizon. A listener hears a sharp, percussive crack with no storm in sight, because the storm is simply too far below the horizon to see, even though its thunder has arrived intact. A second mechanism is shallow offshore seismicity, similar in spirit to the Moody's case, but happening beneath the seafloor rather than under dry land. Small earthquakes with epicenters under the ocean can generate acoustic waves that travel through the water and couple into the atmosphere as they reach the coast, producing a booming sound with a real physical source that is simply invisible, sitting beneath the seabed rather than anywhere a person could look toward. This mechanism is thought to account for a significant share of the coastal mist poofer reports specifically. A third candidate is the bolide, a meteor large enough to survive entry far enough into the atmosphere to explode with real force, sometimes releasing as much energy as a small conventional explosive, producing a shockwave that reaches the ground as a sharp crack or rolling rumble. A bolide entering during daylight can be effectively invisible against a bright sky, leaving sound as the only evidence anyone on the ground actually registers. The infrasound network built for treaty verification detects bolide airbursts on a fairly routine basis, and a meaningful share of them correlate with Skyquake-style reports collected independently. A fourth is distant volcanic infrasound eruptions, sometimes from remote or even submarine volcanoes thousands of kilometers away, capable of producing atmospheric pressure waves that travel intact across enormous distances and arrive as an audible boom with no visible plume anywhere near the listener. The eruption of Krakatoa in 1883 produced a sound documented more than 4,000 kilometers from its source, an extreme case, but proof that the basic physics scales to genuinely vast distances when the initial event is large enough. None of these mechanisms, taken alone, accounts for every report. Some skyquakes occur far from any ocean and any record of local seismicity. Some occur with no atmospheric inversion present at all. Some occur on days when the global infrasound network detects no bolide anywhere near the reported time or location. The category of unexplained skyquake persists after every known mechanism has been checked and ruled out for a given event, because something genuinely does remain, a sound that should not have been there, arriving from a sky that gave no other sign of producing it. The emotional register of a skyquake is worth noting on its own, not as evidence of anything but as a recognizable feature of how people actually experience the overhead world. People who hear them describe a particular kind of unease, distinct from the fear a thunderstorm or an earthquake produces. A thunderstorm has visible architecture clouds, lightning, rain that makes it sound legible, explained by what the eye can also confirm. An earthquake, however frightening in the moment, has an intelligible sensory logic. The ground moves, so something must have moved it. A skyquake offers neither. The sound arrives from an empty sky, and the emptiness itself becomes, briefly, a medium capable of delivering force without any visible warning at all, which runs against a fairly deep assumption most people carry, without ever stating it, that the sky is backdrop, not actor. That unease is not irrational. The atmosphere is a genuine physical system, capable of storing and transmitting energy across distances that dwarf ordinary human perception, and the same atmosphere that produces the Schumann resonance, that cools and contracts under the influence of carbon dioxide, that occasionally strips satellites out of low orbit during a solar storm, is also entirely capable of producing sounds whose precise origin cannot always be traced after the fact. The skyquakes are, in that sense, a reminder that the fluid shell wrapping the planet is in constant, energetic motion, and that most of that motion passes completely unnoticed, below the threshold of ordinary attention, until occasionally, briefly, it does not. None of this is new, in the sense that matters here. The Barisal guns were almost certainly booming over their delta, long before anyone built an industrial economy, long before the carbon dioxide concentration began climbing, long before the inner core paused or the magnetic pole began its current sprint towards Siberia. The Moody's noises predate European contact with the region entirely. What has changed is not the phenomenon but the listening, the seismometers, the satellites, the infrasound arrays, the global network of sensors that has quietly turned the entire planet into a single, continuously monitored instrument. We are documenting more of these events not because the planet has become noisier, but because, for the first time, someone is actually keeping a record everywhere at once. And the record we are keeping is revealing, again and again, that the planet we thought we already understood is still producing signals no one has finished interpreting. The researchers who study any of this infrasound, physicists, atmospheric acousticians, the seismologists who finally explained Moodus after 3 centuries of folklore, tend to work in a field that remains genuinely young by the standards of most established sciences. The global infrasound network was built for a single, narrow purpose, entirely unrelated to any of this, and its usefulness for studying natural phenomena is a secondary, almost accidental benefit. There is no dedicated Skyquake observatory anywhere in the world, no funded mission built specifically to chase the Barisal guns or their counterparts elsewhere. The subject sits at the edge of institutional science, too transient and too poorly funded to support large dedicated programs, too persistent and too well documented across too many independent cultures to dismiss outright. It survives, for now, on a small, scattered community of researchers, trading reports and waveform data, slowly building a taxonomy for things that, individually, refuse to repeat on anyone's schedule. And the sound persists regardless. Somewhere, on an otherwise unremarkable afternoon, a window will rattle, and someone will step outside and look up, scanning an empty sky, and find nothing there to explain it. The sound will fade, the afternoon will return to its stillness, and the planet, having spoken for a moment in a frequency it is possible to hear but not always possible to interpret, will go on about its business, indifferent to whatever curiosity it happened to leave behind, in whoever was standing there to notice. Which brings us back to where we began, 5,000 kilometers beneath you. The iron sphere that helps generate the magnetic envelope around the Earth is turning the other way. It began doing this sometime around 2009, as near as the seismologists can tell, and it has continued doing it ever since. The sphere is roughly the size of Pluto. Its surface is as hot as the surface of the Sun. It is suspended in an ocean of liquid metal that convects with a violence no human eye will ever witness directly, and it is spinning slowly, imperceptibly from up here, but measurably in a direction opposite to the one it followed for decades before. The seismologists who found this are still arguing about what it means, in the same patient, unresolved way. Inga Lehmann once argued for a solid inner core that the prevailing model of her own time said could not exist. Xiao Dong-song, who first detected the core's rotation in 1996 and the pause in 2023, sees evidence of a long-term change in the relationship between the inner core and the mantle above it. John Vidale, working from the seismic echoes of nuclear test explosions, sees an oscillation, a 6-year cycle that will, on his model, bring the core back around. The argument is not settled. The data are still arriving. The seismometers are still recording. The next paper is already being written, and the one after that will add some new constraint, complication, or refinement no one has thought of yet. This is how it has always worked at the edges of what the Earth lets us see directly. Not a single final answer, but a slow, careful narrowing of which stories the evidence can still support. What we know for certain is only this much. The core changed its motion. The field it generates is weaker than it was 200 years ago, and weaker still over one growing patch of the South Atlantic than anywhere else on the planet. The pole that tracks the field's shape is moving towards Siberia faster than it has moved in centuries. The planet's rotation briefly sped up in a way no one alive had measured before. The atmosphere, the ocean's largest current, and the animals that navigate by the same invisible architecture are all, in their own ways, registering some version of the same underlying change. None of these facts, on its own, tells you what is coming next. Taken together, they tell you that the planet you are lying on right now is not a fixed stage. It never was. It is a body, with a heartbeat most of us were never taught to listen for. And tonight, for a couple of hours, you have been listening anyway. You, lying in the dark, have magnetite in your brain. The crystals are there, in your neurons, identical in structure to the crystals that guide a whale across the Pacific or a loggerhead turtle back to the exact beach it hatched on decades earlier. No one can tell you with confidence what they are doing. The experiments that have tried to find out have produced small, inconsistent results. A flicker of altered brainwave activity when a magnetic field shifts around someone in a lab, present in some people and absent in others, real in the data, and far short of anything you could call a sense. What the magnetite does suggest, plainly, is that you are not separate from any of this. You are made, in part, of the same minerals the rest of this story has been tracing from the core outward present in your own skull embedded in the same invisible architecture that has been here since long before anything with a nervous system existed to wonder about it. The honest position, after everything this story has laid out, is not certainty. It is attention. The core paused, and we do not yet know whether that is the early stage of something larger or a 6-year wobble that will quietly correct itself before most people ever hear about it. Either way, the instruments keep running, the seismometers keep recording, the satellites keep mapping a field that keeps moving out from under them. Somewhere on the planet right now, a researcher is comparing this month's reading against last month's, the way people have been doing, in one form or another, since Gauss organized the first network of observatories to take the same measurement on the same day, in different countries, just so the results could finally be compared. We are alive at the moment the heartbeat changed. Good night.